Hello everyone. Today in this video lecture we'll be learning two topics. So in first topic we'll be learning about double crucible fiber drawing process. So in the last video we have seen how a normal fiber is drawn from the preform. Okay, that technique is a general method that is being used to draw the fiber from the given preform. Okay, for large scale manufacturing of optical fibers, we'll be using double crucible fiber drawing process. Okay, so in this double crucible fiber drawing process, as you can see from the figure, we have a inner crucible and outer crucible. Okay, inner crucible, a crucible is nothing but a container that is being used to store a particular dopant or a material, and that is subjected to very high temperature. Okay, so in the inner crucible we can see three crucibles here. Okay, 1, 2 and 3. One inner crucible, another two crucibles that are outer crucible. Okay, so to the inner crucible we will be giving the core preform, and to the outer crucible we will be giving the cladding preform. Okay, and this crucible is subjected to high temperature or induction heating through the two furnaces. Okay, so you can see on the figure there is heating being happening at the different sides of the crucible. As a result of this heating, there are reactions that occur in the reaction chamber, and finally we can draw our optical fiber out from this. Okay, since we are having core as a core in the inner preform, the fiber will be having core in the middle, and cladding will be surrounding the core, since we are giving core preform to the inner crucible. Okay, now we are getting the optical fiber drawn optical fiber out from the heating furnace or the burners. Okay, so the coming fiber has to be checked for the thickness. The thickness is being checked by the thickness monitor, and it is being put to the desired amount of thickness that we require for a particular application. Further to the check-in thickness, we are being this fiber is being put to the coating curing oven. The coating curing oven is nothing but the protection of the optical fiber is done through various coating techniques. So once we have a fiber out with a specific core and a specific cladding refractive index, now we have our thickness monitor, which will measure the thickness, and that thickness measured fiber is then put for different types of coating for the protection of the optical fiber, and finally it is being rolled up in a drum. So in the drawing process we have seen there is a intermediate process for coating. Coating is nothing but a layer of protection that is being given to our optical fiber. Since our optical fiber has to be laid in various environments, we have to see that we should make a optical fiber protective to such environments. So in order to protect our optical fiber, we will be providing two coatings, a primary coating and a secondary coating. Okay, so the main aim of the primary coating is to protect our fiber from bare glass. So our optical fiber is bare glass. It's made from silica. No? So it's a type of glass. So we have to protect this glass from abrasions and other surface contaminants. Okay, so to protect our optical fibers from abrasions and other surface contaminants, we are providing a primary coating. Okay, in spite of this primary coating, we are giving another type of coating called the secondary coating. Okay, this secondary coating protects our optical fiber from mechanical damages. Okay, mechanical damages also, as I already mentioned, if we are laying our optical fiber on a road, there will be a lateral pressure that is happening into our optical fiber. So in order to protect any defects causing to this mechanical or the lateral pressures, we will be applying another type of coating to our optical fiber called the secondary coating. Okay, so basically to our optical fiber we have two types of coating, a primary coating and a secondary coating. Okay, in spite of these two coatings, we are giving an additional protection to our optical fiber by providing a buffer material. A buffer material is nothing but a type of material which is inserted in between the primary coating and the material, so as to provide additional mechanical protection for our fiber, and it also helps to preserve the fiber's inherent strength. So as you can see from the figure, we have different types of buffer coating that are being available. That is tight buffer, loose tube, and gel filled loose tube. So the first figure A, you can see from the figure A, we have a fiber. Okay, onto the fiber we are giving primary coating as well as secondary coating. In this figure we have already mentioned primary coating. Sometimes we give primary coating, sometimes we give both primary and secondary coating depending upon our application of the optical fiber and what type of protection we are expecting for a fiber. Okay, so we have a fiber, we have a primary coating. On top of the primary coating we are giving the buffer. Okay, buffer is nothing but a material that provides additional mechanical protection to our optical fiber. Since it is fitted to our fiber, it is called tight buffer. Okay, so in the figure B, letter B, you can see loose tube. Okay, in loose tube, you can see optical fiber marked in red. On top of the optical fiber is a primary coating. Okay, so after the primary coating, we have certain vacant space which is being filled with air. Okay, on after some space is that we are giving a buffer jacket. Okay, which is denoted by loose tube. Okay, so that the thing in white is air. Okay, so we have a optical fiber. On top of the optical fiber we have a primary coating. Okay, after the primary coating we have air. Okay, air, some space in air. After some space is what we are giving a buffer jacket. It is not tightly bound to the primary coating or the optical fiber as in the above case. Okay, the third one is gel filled loose tube. Okay, in gel filled loose tube, the only difference is that in spite of air, we are giving a gel. Okay. Okay, so we have a optical fiber. On top of that, there is a coating, primary or secondary coating. On top of that, we are giving a gel. On top of the gel is our buffer jacket that is being coming inside. Okay. So as we all know, most of the fibers are made from silica. So the fibers that are made from silica has certain limitations. Is that when you are using fibers made of silica for optical communication, for every 50 to 100 kilometer, we require optical amplifiers to compensate for the losses. As we already studied in the light wave system, for a distance of 50 to 100 kilometers, if you are using silica fibers, we require amplification, optical amplifier, so that the signal is not lost and also to compensate for the losses. And also the fibers made from silica has dispersion, has crosstalks, has bending losses, has tunability. Tunability is a factor that is related with the index, that is refractive index. So when the fiber is being designed, we have to consider the tunability of the fiber. So when we are using silica fiber, there are limitations in the tunability of silica fibers. So because of these limitations of silica fiber, we are going to another type of fibers, that is photonic crystal fiber, PCF. Photonic crystal fiber. Photonic crystal fiber has many advantages over these limitations of silica fiber. So we are going or moving ahead with the photonic crystal fiber nowadays. Okay, so we'll see what is photonic crystal fiber, how is it manufactured. We'll see things like that in the next slide. So, the new classification of fiber is photonic crystal fiber. The photonic crystal fiber is a new in fiber. This was developed in 1995. So, 1995 means a little recent, and it came into manufacturing in the year 2000. So, there's a new type of fiber that is being used in the manufacturing units. That is a photonic crystal fiber. So, what is photonic crystal fiber? Okay, photonic crystal fiber. In the normal fibers, we are using total internal reflection to guide our light. But in photonic crystal fiber, we'll be using total internal reflection, but also photonic band gap effect. Okay, we'll be using these two effects to guide our light through our optical fiber. So, what is this photonic band gap effect? Photonic band gap effect corresponds to the reflection of light by a periodic object. Okay, so there is a periodic object in the so when light touches this periodic object, and if the wavelength with which the light is touching, the half of the wavelength of the light is equal to the period, okay, the periodicity of the object, then it allows the light to pass through that fiber. Okay, so why this light, a half wavelength light, when touching the periodic object, when this half wavelength is equal to the periodicity of the object, it propagates. This is because of the scattering that happens in the periodic object. So if a ray of light whose wavelength, half wavelength, is not matching the periodicity of the object, then that light won't be propagated through the fiber. Okay, so that is the basic idea behind how the light is being guided in a photonic crystal fiber. The photonic crystal fiber is also known as holy fiber or microstructured fiber. Why holy fiber? Because as you can see in the picture, there is a lot of holes. So it's called a holy fiber or microstructured fiber. So when considering the structure of PCF, it is constructed in such a way that it has a lot of internal capillaries that has been filled with air. So you can see a lot of holes. The holes can be considered as capillaries, and these capillaries are filled with air, and they are laid to form a hexagonal structure, that is hexagonal lattice. So you can see a hexagonal lattice structure where you have capillaries, and the capillaries are filled with air. So it is not always necessary that the lattice structure should be hexagon. It can be of different shapes depending upon the manufacturer who is manufacturing the photonic crystal fiber. So the light can propagate along the fiber in defects of its crystal structure. So this light is being propagated through a fiber in the defects of its crystal structure. Okay, so this is the basic principle how a light is being guided through a photonic crystal fiber. So photonic crystal fiber is there in two types. One is index guided fiber and the other one is photonic band gap fiber. So as you can see from the figure, you can figure out the basic difference between an index guided fiber and a photonic band gap fiber. In a photonic band gap fiber, you can see a center there is a hollow portion or a circle portion with white. So that means a core is air. Okay, the core is air in photonic band gap fiber. So the main difference between index guided fiber and photonic band gap fiber is that the core is air in photonic band gap fiber. Okay, so in photonic crystal fiber, the light is propagated depending upon the lattice structure, the placement of air holes. Depending upon the structure and the periodicity of the object, the light is being propagated inside a in a photonic crystal fiber rather than using total internal reflection, where the core and the cladding refractive index comes in as a major role. Okay. So index guided fiber is similar to conventional fiber. So here we have a higher core refractive index which is being surrounded by a cladding. Cladding has different holes, the holes that are being given to the lattice capillaries or given to the lattice structure. So to inside these holes we will be giving different materials or gels. They'll be having a particular wavelength and periodicity. So depending upon the periodicity and wavelength of that light, they will be having a particular refractive index, and the refractive index of this depends upon their wavelength, their size, and the pitch of the holes. Pitch of the holes is nothing but the distance between one hole to other hole is called pitch of the hole. So depending upon all these factors, the refractive index of the cladding depends. Next is photonic bandgap fibers. In photonic bandgap fibers, the light is guided by photonic bandgap effect. The photonic bandgap effect has already been explained.